So now I'm going to illustrate, mostly for those of you who may not be perfectly familiar with this kind of thing. A simple example of Bayesian estimation, but which, as simple as it is, still underlies a large part of what's done in the practice of assimilation of meteorological and oceanographical observations. So I consider for a situation we want to determine a quantity x. Generally speaking, x, whether a scalar or vector, will be the unknown. Quantities or vector of quantities to be determined. And the available data will be denoted either by z or y, depending on the situation, not depending on the situation. To become more explicit, when it is z and when it is y. And I suppose that the information that is available simply consists of two numerical quantities. Z1, which is equal to x plus some quantity zeta1, which I don't know, of course, and Z2, which is equal to x plus zeta2. And since I must make a hypothesis to do something, to do anything, I don't know zeta1 and zeta2, but I assume that zeta1 and zeta2 are realization of particular probability distributions, particularly Gaussian distributions with expectation 0 and respective variances S1 and S2. So that the distribution probability density for zeta1 is P of zeta1 proportional for some coefficients which are not needed. 1 over square root of 2 pi square root of S1, but I want to let, times the exponential of minus zeta1 square plus over 2S1. And same thing for zeta2 with variance S2. And I suppose that the two random variables zeta1 and zeta2 are independent. Z1 and Z2, Z1 and Z2, Z1 and Z2 may be measurements. One zeta1 may be some statistical estimates from previous knowledge on X and Z2 recent measurements. But doesn't matter for what I'm saying. Where Z1 and Z2 come from is irrelevant for what I'm saying. Just they are available. And I wonder, what is, I choose a quantity psi, and I have the question, what is the probability that the unknown quantity x is equal to psi? And I say that if x is equal to psi, then it must mean that zeta1 is equal to z1 minus psi, and that zeta2 is equal to z2 minus psi. The probability that zeta1 is equal to z1 minus psi is proportional to the exponential minus z1 minus psi squared over 2s1 over 2s1. And the probability that zeta2 is equal to z2 minus psi is proportional to exponential z2 minus psi squared over 2s1. And so my unknown probability is proportional to this product. Proportional. It's not necessarily equal to the product of the probabilities, even taken into account the 1 over square root of 2 pi. Because these probabilities integrated over all sides, must sum up to 1. So normalizing the coefficient to put on the denominator. But coefficient is irrelevant for my computation. And so here I do the algebra. Exponential of this times exponential of that is equal to the exponential of this plus that. and I do the algebra, and I compute the term psi, go and do the algebra, and I found that all that is proportional to the exponential of psi minus xa square over 2s, where s is the quantity 1 over s is 1 over s1 is 1 over s2, and psi xa is the weighted average of z1 and z2, z1 over s1 with z2 over s2, times a coefficient, what is 1 over s1, 1 over s2, is times s. And that is the probability distribution for a Gaussian variable with expectation SA and variance S. So the conditional probability distribution for x, 9, z1, and z2 is a Gaussian probability distribution. So how does it look like? I do here. So now, I have here z1 associated with this Gaussian, which I suppose to be a rather flat. Let us pretend this is the Gaussian. I have Z2 with the Gaussian, which I assume to be much sharper. Like that. And so, here for XA, yes, come on. Now I know will be X. The estimated quantity will be XA, while A for analysis or assimilated. So XA will systematically be the estimated quantity, and X the real unknown quantity. So XA is a weighted average with larger weight to Z2, which are the smaller variance, so it is somewhere here. So XA is here. And it is associated with the Gaussian, which has variance 1 over s equal to 1 over s1, 1 over s2, which means that s is smaller than both s1 and s2. So it is still a sharper Gaussian. So it's still a sharper Gaussian. So this is the solution of this problem. The conditional probability distribution for x given z1 and z2 with Gaussian probabilities, with z1 and z2, z1 and z2 having Gaussian probability distribution with variance unbiased with variance s1 and s2 is the Gaussian probability distribution with expectation xa and variance s. Okay, so XA is a weighted average of Z1 and Z2, with a larger weight being given to a more accurate of the two estimates, Z1 and Z2. S is smaller than either S1 and Z2. The uncertainty, if I accept, as I said, the uncertainty is measured by the variance. If the uncertainty is measured by the variance, the uncertainty and the estimate is smaller than the uncertainty in either one of the two a priori pieces of information. Incidentally, S is independent of the values Z1 and Z2. So at one, I repeat this process many times with the same laws for the errors, but with different values of Z1 and Z2. I repeat that every day. The conditional probability distribution for XA, for X, will be shifted in space, but the shape will remain the same. Okay. So this is what is in here actually. Okay, yes, Z1 and Z2, Z1 and Z2 mutually independent. What is the conditional probability? That is equal to some value psi. Okay, so that's it. distribution. So, do the computation and like that. The conditional probability distribution do is Gaussian, capital N here means Gaussian probability distribution like expectation XA and variance S, and S, which is smaller than both S1 and S2, is independent of Z1 and Z2. So this is the sequence. It shows how we can, in principle, compute the conditional probability distribution on the basis of uncertain information, provided the uncertainty is described by a probability distribution. Okay, so as a remark, I consider again the same problem, similar problem. Z1 equal x plus zeta 2, x plus zeta 2. But now, zeta 1 and zeta 2, instead of having Gaussian probability distribution, have exponential probability distribution. Exponential minus zeta over A. That is the flow of the error. Probability distribution of the error, like that. With an angle at this point, an exponential decrease. Zeta. I don't claim this empirically, it's just an example. You do the same thing. And you find, and you suppose that the parameter A, which defines the width of this probability distribution, actually the variance, so that is 2A squared. I suppose the parameter A is the same for both zeta 1 and zeta 2. And I find, not surprisingly, that the expectation is zeta 1 to zeta 2 over 2, of course. The problem is symmetric with respect to zeta 1 and zeta 2. Z1, 2. Your XA is just in the middle. But the conditional probability density is, it is uniform over the interval Z1, Z2. The conditional probability density like that. And then decreases exponentially with parameter 2A outside of the interval. It is sharper, decreases more sharply than in either one of the two original measurements. So, certainly different. The conditional probability distribution is not of the same algebraic type or functional type as in the Gaussian case. But what is worth mentioning is that the variance of the solution of probability distribution now it depends on the value of Z1 and Z2. Contrary to what was the case in the Gaussian situation. It depends on the value of Z1 and Z2. And not only does it depend on the value of Z1 and Z2, but it actually can become, it is unbounded, depending on the distance Z1 minus Z2. It can become a bad variance. The variance of the conditional a posteriori conditional probability can be larger than the common variance of the error. If that looks surprising to you, and it was surprising to me the first time I realized that, it means that you implicitly have a Gaussian view of things in your mind about probability distribution. This is to be absolutely obvious. It is not necessarily true. It is totally one quantity which always goes the right direction, so to speak, is the entropy. Integral of P over 3 over 3 probability. So it's the right direction. That's not the variance.
So would that mean, though, that it's actually not helpful to have two measurements like that? Or to have, I mean, if you have a larger spread at the end of the day.
It means that, well, for this kind of probability distribution, the variance is not a good measure of the uncertainty.
Okay.
In fact, in the case of a Gaussian probability distribution, the entropy is a simple function of the variance.
Right, yeah.
Okay, so that was just a remark to point and respect in which. So I can't
this is just a general question. So for non-Gaussian distributions, a lot of time we look at them and we want to think about uncertainty in them, say like a bimodal distribution. Should we think about it in terms of, say, a measure like entropy?
Yes, maybe like although entropy is much more difficult to compute and actually manipulate.
Yeah.
And as I said later, largely, to a large extent, what we have used is based on linear symmetry, which is a generalization of a Hilbert, and which achieves Bayesian estimation in the case the errors and the data are linear and Gaussian. But I can say right now that if it is the scheme that I use, it is because they are, in a sense, the most practically convenient. They are the simplest or non-simplicist schemes. That's why I still use largely Gaussian methods, even though we perfectly know that our errors, what matters probability distribution, errors and the uncertainty of the data, even though we know these probability distributions are not Gaussian. Yes.
What is the meaning of always? Does it mean independently of the P1 and P2?
Yes, yes. Whatever, if you combine, if you compute entropy with entropy of the condition.
Decrease independent of P1 and P2. Is there any other quantity that decrease?
What is that?
Is there any other quantity that decrease? Like
Well, does it decrease?
It could be unique in that sense.
In this direction it goes, but it always goes the same direction.
But is there any other, in that sense, entropy is unique or any other quantity that decrease? Is it
unique?
Yeah.
What is it? It is uniquely defined. Yes.
Unique means, is there any other quantity that decrease by combination over P1?
Yes, it always goes the same way. Whether it is an increase or an increase.
So there are other quantities. Like
it goes the same direction.
But he is asking for other qualities,
okay.
other than entropy.
yes.
Oh, other
Covariance goes the other way around, you said.
Okay. Other quantities for entropy, which, I'm not sure.
There certainly are, but they're mostly trivial. I mean, the quantity 0
yes.
obviously is a decrease in uncertainty. So, if you had a rule that always assigned 0 after conditioning, then you satisfied it. So entropy is not the necessary and sufficient measure in that sense. We can easily find others, but whether they truly represent our uncertainty is a more difficult thing to say.
Okay, so now let's come more generally to Bayesian estimation. I consider a state vector x, which is my number, and I suppose I have a set of data z, that's a number, finite number, state vector of finite dimension n, which is my n, and I have a finite number of data, making it vector z, of a form, some function which I know of x of zeta, and zeta is a random element which meant it represents the uncertainty of the data, or more precisely, of the link between the data and the element vector. For instance, an example could be z equal gamma of x plus zeta, where gamma is a known matrix of coefficients, and zeta is error, which might be Gaussian. And that's the question. What is the probability that x is equal to psi? X is equal to psi, z is equal to f of psi zeta. And then the probability of x being equal to psi zeta is the probability of z equal f of psi zeta, thereby normalized by the integral of this quantity over all psi. And this is unambiguously defined if for any zeta there is at most one x such that f of x of zeta equals z. If there are two x's, which is defined by a variety condition, of course, the corresponding zeta, the probability for the corresponding zeta we don't know how to share it between the various values of the x, which are compatible with both zeta and zeta. Which means, and this condition is a determination condition, which means that the data contain information, either directly or indirectly, on any component of x. That's just... Okay. Bayesian estimation is already possible in the general theoretical form, in meteorological and national numerical application, because first of all, it is simply impossible to explicitly describe the probability distribution in a spatial dimension, even as low as, I think, 1,000, not to speak of a dimension 10 to the 7th or a 9th of present numerical weather prediction models. We want to explicitly and completely describing probability distribution in a very large dimension. We simply cannot do it. We can have approximate formula. We can assume a probability to the distribution to be Gaussian. But even Gaussian, we have to define the covariance matrix, which has this dimension with dimension n times n. So, and if we don't know anything about the probability distribution, and we want to describe it, we cannot. And in any case, the probability distribution for errors on the data are very poorly known. And the error in particular, the errors on the model. These numerical models I've been talking about, actually, as I told you, evolved permanently. In the meteorological center, like ECMWF, or the meteorological services of many countries, there is a model, or there are models, which evolve continuously. There is no week, or at least certainly no month, the modification is made somewhere on the model. And it is easy to show that the time necessary to accumulate significant statistics up to the performance of the model, so to obtain some rough description of the probability distribution of errors in the model, meaning the model as a simulator of the atmosphere, is much larger than the time of the model, by several orders of magnitude. So as the models evolve and improve, but in most of the time improve, much faster than the time necessary to actually evaluate in a reliable way their performance. We can evaluate sufficiently well to show that they improve, as was shown by one of the pictures I showed during my first lecture. But, and if we improve, the model improves, it's because of two things. First of all, the computer power constantly increases, at least so far. And so meteorologists have always used, since the very beginning of electronic computers, actually numerical weather prediction dates back to the development of the first electronic computers. It was scientific development of electronic computers with in mind scientific applications was done due to a large part to John von Neumann in Princeton in the late 40s. And among the scientific applications he had in mind was numerical weather prediction. It was one of the particular scientific applications von Neumann had in mind. And he set up a group of people who in Princeton who worked specifically on numerical weather prediction. And the group, after von Neumann died, moved to somewhere else. The names of the people, Joe Charney, which you know the name of whose name you may know, was the member of the group. Norman Phillips, was still alive, was the member of the group, and other people. And so, yes, the models improve because, first of all, the computing power increases consequently, and meteorologists have always used the available computing power by increasing the resolution of the model. And this has proved to lead to an improvement of the forecast. The other thing is that meteorologists always introduce, not only increase the spatial resolution of the model, but also introduce in the model physical processes, which, for instance, to take example with a picture, maybe I'll show you on the which a simple picture of all of a number of physical processes which are introduced in the model. For instance, in the first model, clouds, liquid water in the form of droplets, was not even introduced in the model. Clouds with very significant radiative effects were progressively introduced in the model. Water at the surface of the Earth, whether water in the ocean or water in the soil, which can evaporate or even in liquid form be transported in the atmosphere, which the amount of which can also increase because of precipitation. In the first models was not represented. Now it is represented, actually there are several layers in large meteorological model. There are several more layers in the soil with possibly different with water content for each of these, which can be transported, which can evaporate. Precipitation increases by the water content of the soil, and water which fall for precipitation can actually flow downwards, then flow to some other areas. So flow by river now introduced in model, but that is relatively recent. And new meteorologists constantly introduce new physical processes. This is how models are improved. And it happens occasionally that one particular defect is identified in the model and then it's corrected. What also happened that one particular defect is identified, it is corrected, and the result wasn't before, because several defects tended to compensate mutually. It's a situation which is common, and in a sense very unpleasant. It's very unpleasant, it is very difficult to correct. Anyway, we don't know the probability distribution of errors on the model, so we could not implement something like that by assuming that the model error is Gaussian or anything with the particular attributes. And so, in practice, we have to restrict ourselves to a much more modest goal. And I can say that two approaches exist at present. One is to obtain some central estimate of a conditional probability distribution, something which usually is understood as being the mean of a probability distribution of probability. It can be removed. It will be denoted SA, as I said, automatically, whatever it is. Plus, in addition to that central estimate, some estimate of the corresponding price, standard deviation, possibly a number of the cross correlation between the different areas. And the second approach is to produce an ensemble of estimates which are meant to sample the conditional probability distribution. These are ensemble methods in which the final output is not one central estimate SA plus a measure of the associated uncertainty. It's not XA, it's not like in this example, XA plus S. It is a number of points in state space which are meant to sample the conditional probability distribution. These points may be equal, have all the same weight. They may have different weights, measuring the individual probability. I say from the start that the size of the ensembles is typically in the range a few tens to a few hundreds, which might seem ridiculously small in comparison with 10 to the 7th or 10 to the 8th dimension of modesty. Anyway, for many reasons, particularly for reasons of available computing power, these dimensions are included. And this, of which I won't say much, exists in two forms. The ensemble Kalman filter, which we dealt with by Pavel-Sakov, so I think this afternoon, and now particle filters, of which I will speak in my last lecture on that subject. So I say, okay. I mentioned also that the proportion of resources that are devoted to assimilation, numerical weather prediction, has steadily increased over time. At the very beginning of numerical weather prediction, so I thought numerical weather prediction was started, numerical modeling of estimate flow was started in a group headed by John Byman in Princeton in the late 40s. The first meteorological prediction was actually performed here in Stockholm, the Swedish Meteorological Service. I don't know exactly the date, maybe someone, I think it's 1955. The first actual forecast, when model did run into the future. And at that time, the definition of initial conditions was considered as just nothing. It was just, there were a number of meteorological stations which transmitted observations, and there was a grid for a model, and it was simply a matter of transforming the measurements in the meteorological station to grid points, and that was just a simple interpolation process, and it was considered as simply nothing in comparison with the real thing, which of course was running the model. That was, of course, the real stuff. And the definition of initial condition. And little by little, it took them that after all, it might be worth to devote more resources to the definition of initial condition. One of the first problems was not by doing simple interpolation and doing integration. When people started using models of realistic physics, irrealistic oscillations occurred in the temporal integration. First, people thought it was a numerical artifact. Turned out it was not. The oscillations were physical processes, gravity waves, oscillations, which occur in the atmosphere, for instance, in the vicinity of mountains, or even in the vicinity of intense convective cells. They are used by people who glide in the and saying that gravity waves are almost absent from the atmosphere, and meaning that the absence of the atmosphere is essentially equivalent to saying that the atmosphere is a geostrophic band. So if you think about that, in my first lecture, it was necessary to filter out this gravity. And then came the problem of observations coming in constantly continuously in time, the satellite observations, are widely available in the late 70s. Well, after the first problem, it was to carry information from the past to new observation, even in the case of synoptic observations. At a given time, given synoptic time, let's say 0 Greenwich time, 0 UTC, there are two things were available. First, the forecast made from the previous time, from the day before, plus with the observation. It was necessary to combine them. So the situation was not as simply interpolating from stations to grid points. Incidentally, the word analysis, which is used for meteorological analysis, comes from what was done before computers were available. At that time, but it's still now, meteorologists and forecasters, basic material, working material, was charts. Charts, as you see, newspapers, charts, isobars, drawn by hand. What the meteorologists did was produce a chart of the present situation, a few hours later, situation at 12 UTC, produced that in the afternoon, and from a chart, he made a forecast for the following day or 2 days, which he drew by hand. Then, the following day, he came back to work, took the chart he had drawn the day before, then plotted the new observation that had come in real time on this chart, and did what was called the analysis of the situation. What was a highly subjective process in which some forecasters were better than others. No doubt, but it was highly subjective. And by combining the forecast made by hand, plus the new observation, he drew a new chart of a present situation, for which he did the new forecast. And what was doing in the analysis. And when computers were available, of course, what people did was to ask the computer to do automatically what they used to do by hand, to do it more rapidly. And then came up the expression of objective analysis. For a period, the ancestor of what I'm going to talk about was called objective analysis because it was done objectively on a computer with a well-defined numerical algorithm. Our opposition to the subjective analysis made by experienced forecasters. Of course, as you imagine, many forecasters said, oh, objective analysis will never do as well as my experience, will never do as well as my subjective analysis. It is true that some people were perfectly able to do, to beat the computer. In the first period, like chess players, for a long time, were able to beat the chess software. Not anymore, but the chess players the chess software. Exactly the same. And so obviously now the word analysis has come in. The word analysis is both the process by which the description of a flow is obtained, and the word assimilation is used in a context where the temporal evolution, physical laws for the temporal evolution of the process are explicitly taken into account, and the analysis is also the final description of the flow. And the figures I showed you, the observed situation was described not as observed, but analysis, stressing, but it was not pure observation. It had gone through a process, all kinds of things, numerical process. So that's for the origin of the word analysis. And to come back to what I was saying, yes, I told you, in 1950, 1955, determining the initial condition in comparison to integrating the model was just nothing. Now, at now, 1 year ago, at TCMWF, the cost of 24 hours of assimilation was half the global cost of a 10-day forecast, including the ensemble prediction that we're talking about. And I think this proportion is increased because in the meantime, TCMWF has introduced an ensemble variational assimilation, of which I may be able to speak a little bit. And this has increased the proportion of computer resources devoted to assimilation. So the definition of the initial conditions now must be something like close to the cost of a 10-day forecast. As much resources, almost as much resources, is devoted to 24 hours of assimilation as for 10-day forecast. And this just has come out of the fact that it is a kind of almost, we say, natural selection process. It is profitable, it is useful to devote more resources to more and more resources to the definition of initial conditions. Okay, now at present, assimilation exists in two forms. There is sequential assimilation, in which the numerical model is integrated over the period over which observations are available. And whenever the state of the model, the time of the model, reaches the time at which observation is available, then the state predicted by the model the model is integrated in time, over time, and over time the model reaches an instant at which observations are available. Then the state produced by the model, which in this context is called the background, XB, B for background, is combined with the observation, which I identify, this is combined, plus the estimation, to produce a new estimate, which now is called an analysis, and denoted XA. Then process is started, and progressively all observations available over, for instance, 44 hours period are introduced, assimilated into the model. And at the end of the period, the model is run into the future. So this is what is called sequential assimilation. And the optimal form of sequential assimilation in the context of linearity and Gaussianity is what is the technique of Kalman filter, which was introduced a long time ago, in 1960 actually, in a totally different context, by Kalman and one of several of his students, Kalman filter. And in meteorology, it has taken the form of ensemble Kalman filter, which Pavel Sakov is going to speak about. And the second form of assimilation, I'm talking now only from purely algorithmic description, is what is called variational assimilation. This is what I'm going to speak about. Observations over a given period, typically 24 hours, are taken as a whole, and then the model solution is fitted over the whole period in order which is in order to fit as closely as possible the available observation. So a measure is introduced, which measures the distance between one model solution and the observation, and variational assimilation looks for the initial condition at the beginning of the period, which define the model solution which best fits the observation in terms of that measure, which is really important. And this is called the variational assimilation. This is what I'm going to speak about. Sequential assimilation, as I just described it in this simple form, carries information from the past into the future, but not the other way. Variational assimilation carries the information in both ways. If you want to do forecast, this aspect is secondary, because at the time when you start a forecast, of course, you can have used only observation prior to that time. But if you do, and assimilation is used also for doing that, reassimilation of past data with present computers, with present models, and present in order to obtain, for instance, as accurate a description of the history of the meteorological flow over a period of years, of tens of years. And this is very important in the present context of study of the evolution of climate. Then if I want to re-estimate a posteriori with present computers and algorithm the state of the atmosphere on the 26th of April of 1970, at noon, UTC time, I will use, of course, observation before that time, but also observations before 6, 12, or even 20 hours later. So in that context, a method which carries information in both directions is, for all that aspects, preferred. Okay. So, okay. Yes?
But does not that violate causality?
Your pardon?
But does not that violate causality?
Oh, causality. Causality is embedded in the model equation. We have equation d over dt of something at a given time equals an explicit function of the field's atmosphere at that time. Causality for us, that is the causality. This question of how to propagate information, well, I must say that algorithmically, I speak of that. I speak of it in my later lectures. One uses for doing that what is called the adjoint equations of the model, which are equations which describe the temporal evolution of basically of the gradient of some function with respect to the state of the model. The model computes the evolution. The model exists. Computes basically dx over dt. X is the state of the flow, and it computes the evolution of the flow x over the equation dx on the basis of the equation dx. The adjoint equation computes the evolution of the gradient of d over dt of the gradient of some quantity J with respect to x. That is of partial derivative with respect to the statement. And if, for instance, a process is irreversible from past into the future, the algebraic equation lead to a well-posed mathematical problem for evolution from the past into the future. It is easy to see that the algebraic equation leads to a well-posed problem for integration from the future into the past. And this is how technically, it's just a technical, a numerical, technical aspect. This is how variation of simulation and program is possible. But causality is embedded in the model equation.
For the 3D bar data assimilation scheme, is that both sequential and variational?
Well,
there's no time component in the
yes,
variational.
okay. So 3D bar actually can be different. If we speak simply of the answer is not easy because assimilation is a very technical. The words which are used simply words which should appear at some stage of technical development, and then the technique evolves. So words have remained, the significance is not fully appropriate for representation, actually. But 3D var, now 3D var is sequential, at least can perfectly be used in a sequential process. I said, in sequential assimilation, a background XD is combined with the observation Y to obtain an analysis XA, and a 3D bar algorithm, for those who don't know, 3D bar means three-dimensional variational. 3D bar algorithm can very well be used for doing that. And a 4D bar algorithm does that with an explicit time dimension, not only an explicit time dimension, but an explicit new dynamical model of the evolution of the flow. Because one could take a rather short period of time and ignore the fact that the seed of the atmosphere has evolved over a short time. This is an approximation which is or was rather commonly done. So it has the time dimension, numerical evolution, but dynamical evolution still is enough. 4D bar does take into account a dynamical evolution. Yes, 4D bar can be said. It is artistically used in the sequential environment. Now, 3D bar is very much associated with 4D bar because technically people who have developed 4D bar have gone through the way of developing first 3D bar. So 3D bar has been a point of passage on the way to 4D bar. That's why it is associated with it. In itself, not. It can be sequential. Another question?
You mentioned physical laws which can be embedded in the assimilation process.
Yes.
You mentioned especially geostrophical balance.
Yes.
What about energy conservation, especially when we talk about re-assimilating data for climate purposes?
Okay. So energy conservation. First of all, numerical models don't total energy of the flow, so in different form, internal efficiency, kinetic energy, potential energy. For that must be the evolution of total energy must be equal, variation of total energy must be equal to the input of energy, which is 1.7%, minus what is energy lost by the atmosphere, either radiation to the surface space, or through dissipation at the surface of the country. Models don't exactly consider energy, of course, because in particular the temporal interpretation. I'm not sure whether there is a scheme which is in spatial component. Of course, when there is discretization of the model, there is both the spatial discretization, which is used for computing, if I were the equation of the form d over dt of some quantity a dx of nt is what f of x. X is the spin vector. Incidentally, when writing on the board, if I'm in a vector, I put a bar under it. On my slides, a vector will normally be denoted in both case character. Just something like that. Yes, yeah. On the board, so I have this. F of x is x element time, no delay. So both first a special discretization, which computes as able to compute points, or for every spectral component of the flow, f of x as a function of the present state. This involves, of course, spatial dimension, because there are gradient and dimension field, and so there is a spatial discretization. And there is a temporal discretization, which goes from x with some time t to x with some time t plus delta t. Of course, both are two. And usually speaking, energy conservation properties are not verified by at least the temporal discretization. There is no systematic trend, because there are at least in short period. Now in the assimilation, well, since observations are introduced, the observation very well implied that the estimate of the energy of flow, either of global energy or the energy of the internal energy or kinetic energy in some volume of the atmosphere, is actually larger than what's implied by the model, by the background energy. Yes, it will be normal that the energy is modified by the assimilation. There is a constraint of certain constraint of conservation energy or anything, even mass, actually, even mass in the assimilation. That's normal because the observation, they are what we mean, and they want to say that the energy, the entropy is larger than what implied by it. So there is no enforcement, no attempt to enforce any conservation property, even in the assimilation. I don't know if that answers the question. You are speaking about climatology.
I mean, you did say that there are ways of enforcing, for example, geostrophic balance.
Yes, indirectly.
But of course, if you don't enforce it, it may still be approximately 2 as far as the model is
Yes.
an approximation.
Now it is introduced. Well, that's what it is. There are two ways of doing that. One is simply fundamentally in the process. So say that the error on the background is geostrophic. The error on the background. So this means that the correction made on the background will be geostrophic. So there will be a geostrophic background plus a small geostrophic variation, and this will lead to a geostrophic. Another way, which is called initialization, which is well, which is not appropriate. Is to actually modify the field after assimilation in order to make it more difficult. But I won't speak much about that because it does not have as much importance as it should have, and I think I keep to leave that here completely. The constraint for geography will be introduced in this.
So I guess that is mainly then a matter of luck. If you can take advantage of, by rewriting, for example, the equations in a form that does allow you to make the changes, for example, based certain rules, certain laws. That may not always be possible, but in some cases it may be possible, and it's convenient to.
You mean not to introduce a constraint for the
to enforce it, for example.
Yes.
It's not always.
As much as improved, and the condition for balance is better and better represented by the model. It is a natural thing that little by little the need for actually explicitly enforcing the order of invariance will be less and less important.
I hope, for example, about positivity of certain quantities.
Oh.
I mean, you don't.
Is that a matter of
distribution function?
That's the problem. That's the problem. How we can cross positivity. Well, nice to say. You don't need that. You just make it so. But I said, by and large, what we do is still of Gaussian exploration. Of course, you cannot make it enforce positivity.
But in many cases, it is possible to rewrite the equations, of course, in terms of logarithmic.
Yes, yes, that is done. That is done, yes. That is done to use one way to the logarithm of the quantity.
Are there any other questions? Before we have lunch, let me point out that we have later this afternoon, before the, so at 4:30, between 4:30 and 5:30, after which we have the reception in the Nordea building, we have approximately an hour, which allows us to have some short presentations by students or participants at the school. I've already talked to a few people, but if any of you have some material that they would briefly like to present later this afternoon, even just on the blackboard, by means of introducing themselves and expressing especially their hopes from this, about the school, what they will hope to learn from the school. I think that would be an excellent opportunity today, and it also allows, of course, the lecturers then to get an idea about the level and expectations from the participants. So please talk to me during and after lunch today about this possibility today. Any other questions? So then, I hope many of you have obtained lunch tickets. If you have then you can always pay still downstairs. So, for example, also don't have a lunch ticket. Official participant. You can always sit down in a dedicated area. I think it's not normally safe to leave the computers here. The rules are not locked.
What have you read in idea?
Memory. Because it's not the full machine, but this is the logging node.
No, but I'm on the. No, I am.
Yeah, you log in, go to the logging node. You are not in one of the processes.
BBC says that.